Welcome to Related Rates, Introduction and Example 1 by Conceptual Calculus. In this video, we will learn how to solve the related rates problems that usually follow implicit differentiation in a first semester calculus course. To solve a problem involving related rates, it is important to distinguish between the basic quantities and their rates of change. It may help to consider the units. Whatever units the basic quantity has, the rate of change of that quantity will have those units divided by a time unit, such as seconds or minutes. Once you have identified the basic quantities involved in your problems, represent each one with a variable. Write an equation to describe how those quantities are related. Remember, at this point we are working with the basic quantities, not their rates of change. When you have the equation, differentiate both sides with respect to time. You may need to use implicit differentiation for this step. After differentiating the equation, solve for the unknown rate of change. Then, substitute in the known values of quantities and their rates of change at the moment of interest to get the desired result. Always check your solution. Make sure it makes sense in the problem. Finally, state your result in the terms of the problem with appropriate units. Here is a classic example. Two roads meet at a right angle. Car A is driving 30 miles per hour to the east. Car B is driving at 50 miles per hour to the north. How fast is the distance between the two cars changing at the moment when Car A is 2 miles west of the intersection and Car B is 4 miles north of the intersection? We have information about where the cars are and how fast they are moving. The basic quantity is position, or distance, which is in miles. The rate of change of distance is the velocity, which is in miles per hour. We start with the basic quantities, the positions of the cars. At a particular moment, Car A is 2 miles west of the intersection. But it does not stay there. It is moving. That means the distance between Car A and the intersection is a variable. I'm going to call it x. The distance between Car B and the intersection is also a variable. I'm going to call it y. We are asked to find the rate at which the distance between the cars is changing. We start with the basic quantity, the distance between the cars. I'm going to call it z. We want to find its rate of change. Now we write an equation describing how these quantities are related to one another. Because the roads meet at a right angle, the Pythagorean theorem applies. Our equation is x squared plus y squared equals z squared. Next, we differentiate both sides of this equation with respect to time. This requires implicit differentiation, which is an application of the chain rule. We treat x, y, and z all as functions of t, the time. When we differentiate the square, x squared, we get 2x, but then we have to multiply that by the derivative of the quantity inside the square. That gives us 2x times dx dt. The same applies to the other terms, so our equation becomes 2x dx dt plus 2y dy dt equals 2z dz dt. Next, we solve for the thing we were asked to find. The question asked, how fast is the distance between the two cars changing? Earlier, we gave the name z to the distance between the two cars. So, to find out how fast that is changing, we want dz dt. If we divide both sides of the equation by 2z, then dz dt is alone on one side. Now we substitute the given values into this equation to get a value for dz dt. At the moment of interest, x is 2 miles and y is 4 miles. Dx dt comes from the speed of Car A. Because Car A is moving toward the intersection, the distance between the car and the intersection is getting smaller. That makes dx dt equal to negative 30 miles per hour. Dy dt comes from the speed of Car B. Because Car B is moving away from the intersection, the distance between the car and the intersection is getting larger. That makes dy dt equal to positive 50 miles per hour. We still need a value for z. That was not given, but we can find it using the Pythagorean theorem. We know x squared plus y squared is z squared, so z is the square root of 4 plus 16, square root of 20. The square root of 20 is about 4.47. We substitute 4.47 miles for z and find that dz dt is about 31.32 miles per hour. Next, we check whether that result makes sense. We've found a positive value for dz dt, which means the length of z should be increasing. Is it? We can use the diagram to think about that. Car A is moving to the east at 30 miles per hour, so I'll sketch it a bit to the right of its original position. Car B is moving north at 50 miles an hour. That's not quite double 30 miles an hour, so I'll sketch B farther from its original position than car A was, but not quite twice as far. What does that do to the distance between the cars? It does look a bit longer, so I can believe that it's increasing. This kind of check is most accurate if your sketch is drawn to scale. Other problems call for other types of checks. The key point is that you always consider whether your result makes sense. The last step is to state the result in terms of the question with units. If the question had been, what is the value of dz dt, then dz dt equals 31.32 would be a fine answer. But it wasn't. The question was, how fast is the distance between the cars changing? So, that's the question we answer. We write, the distance between the cars is increasing at a rate of 31.32 miles per hour. Now, we are finished. For another example using related rates, see our next video. Thank you for watching Related Rates, Introduction and Example 1 by Conceptual Calculus.